Hello everyone! Today I will be presenting our work, LensCap, Split Process Framework for Fine-Grained Visual Privacy Control for Augmented Reality Apps. I'm Jinghan Hu, and this work is in collaboration with Andrew Josephus and Robert Lee Camois. Augmented reality, with its unique interactive experience, has been applied to many fields, including education, medicine, entertainment, navigation, and shopping. For AR to work, AR users utilize mobile devices to continuously sense the physical world for virtual object overlays. The physical world is filled with private user information, and unfortunately, in today's AR apps, the user's visual environment can potentially be exposed to third-party entities without the user's knowledge. Those private user information may contain a credit card left on the table, a driver license, top secrets written on the board, and of course, a user's visual identity. Under the current permission enforcement model in popular operating systems, an AR app is given internet permission at installation time and granted camera permission and external storage write permission at runtime by users. Then, these permissions are managed within one application sandbox for its entire life cycle. With this permission granted, a malicious AR developer could silently collect camera frames and the information derived from them for malicious intent, including sending visual data to a private server. To protect users' visual privacy, related works like Darkly system turns camera frames into opaque references, and untrusted vision applications can only dereference them through trusted library APIs. However, everything is still in one application process, thus the camera frames are still vulnerable to be collected. The Oculus Quest camera system prohibits applications from accessing the pass-through camera. Instead, developers are only able to utilize camera poses, controller poses, and hand poses. With these solutions, the challenges still remain because we cannot simply revoke applications' network access or developers' access to the visual data because AR apps need the ability to visually render the entire frame to provide the camera view as a backdrop for virtual AR overlays or potentially communicate with the cloud component. So, how do we protect users from surreptitious collection of visual data while maintaining usable visual computing for AR applications? To address visual privacy disclosure, we introduce LensCap, which adopts split process access control at the application layer. Compared with the legacy one application process, LensCap splits the application into two processes and manages their permissions separately. A visual process having camera permission granted to host developers' visual code, which has full access to vision libraries and camera interfaces. A network process having network permission and storage write permission granted to maintain network communication. Then, visual data can only be transmitted out of the visual process boundary through our trusted LensCap communication services, wrapped around trusted AR frameworks and subject to the user's monitoring and approval at a fine granularity. With LensCap, AR apps and vision libraries are having expressive access to camera frames, and users are allowed fine-grained visual control of the potential transmission of their visual data. In detail, LensCap, Split Process Framework for Fine-Grained Visual Privacy Control for Augmented Reality Apps, functions on four core components: enforced split process access control, secured communication channels for processes to securely exchange data, fine-grained data monitoring, and screen-based overlay composition. Using LensCap implementation in Android as an example, LensCap split process access control sits in the application layer, and it is enforced by extending the legacy permission enforcement in the framework layer. The enforcement guarantees that the visual process only has the camera permission granted, and the network process does not have the camera permission granted while having the right external storage and the network permission granted. The visual process hosts developers' visual code, which has full access to the camera frames. The network process hosts developers' network code, which maintains network communications. Then, LensCap exposes two data handlers, a visual handler for the visual process and a network handler for the network process to maintain data communications. These two data handlers enable a trusted network-to-visual channel and a visual-to-network channel which needs to be secured through LensCap fine-grained data monitoring. This fine-grained data monitoring enforces the usage of trusted AR frameworks and presents user interfaces. Finally, each process is given a screen to render frames and present user interfaces through screen-based overlay composition. Here is one example of the screen-based overlay composition. The visual process screen renders the camera feed and the virtual object. The network process screen presents a search bar, and then the network screen is overlaid on top of the visual screen, and from the user's view, it is exactly the same as the legacy apps. LensCap split process framework enables 4 programming models. Scenario 1, AR camera overlays and spatial interactions. In this scenario, developers can program spatial interactions with the AR scene in the visual process, for example, allowing users to place, spin, scale, and otherwise interact with the virtual 3D object content. In this scenario, the application does not need to request any LensCap permissions, as all visual data can be contained in the visual process. Scenario 2, network requests without visual data needs. In this scenario, developers can program network requests in the network process. This request can be triggered by non-AR on-screen canvas user interface elements like buttons, by time-based events, or by other activities that don't require visual data. LensCap allows network process to influence activities in the visual process through the unidirectional network to visual channel. Similar to scenario 1, the application does not need to request any LensCap permissions as nothing from the visual process needs to interact with the network process. Scenario 3, network requests with visual or spatial information. In this scenario, developers may need to share visual or spatial information among multiple devices for multiplayer positioning, joint illumination estimation, or other cloud-based activities. In this case, LensCap allows developers to request user permission to expose specific AR library outputs over the visual to network channel. For example, developers can explicitly request the camera pose permission in order to use AR positioning data inferred in the visual process for network-based rendering. This scenario also facilitates AR-based spatial interactions that trigger network downloads, as spatial interactions may be inextractable from both visual data and network data. Altogether, in this scenario, LensCap requires users to enable specific visual data to be shared without exposing their entire camera frame. Scenario 4, cloud-based camera frame sharing. In some apps, users may want to send their entire camera frame to the cloud to enable live streaming and social media sharing. Other apps may require cloud-based processing of camera frames for resource-intensive and/or collective vision operations. In these apps, developers can request users to allow camera frames to pass through in the LensCap visual to network channel. For this scenario, users can be made aware that their visual privacy might be leaked and selectively disable camera frame access at their discretion. Furthermore, users can review the LensCap data usage monitor to observe when camera frames are collected to infer malicious intent. We prototyped LensCap as an Android library that can work with standalone Android projects as well as with Unreal Engine projects. In Unreal Engine, trusted AR APIs are provided through blueprint callables. In Android, Visual and Network Data Handler provides runtime services and expose, send, and receive APIs. This is an overall application development example. The user searches the dream car in the search bar presented in the network process. Then the car model is downloaded and applied to the visual process for rendering through the unidirectional network to visual channel. Next, the user is able to interact with the virtual car model presented in the visual process screen. Further, the application requires point clouds to be uploaded for better positioning. The developer needs to request point cloud transmission permission to be granted. If allowed by users, point clouds can finally reach the network process, and when and how often the data is collected can be visualized in the time of collection function. We evaluated LensCap in 5 cloud-based AR apps, all developed in Unreal Engine and running on Google Pixel 4 XL smartphones within the Android environment. These apps require camera pose, lighting estimation, AR point cloud, face tracking result, and the whole camera frame to be shared between devices. In the evaluation, we monitor application performance, which is the time interval between 2 consecutive frames, measured by the delta time acquired from the tick function in blueprint callables, which is called every frame. We also monitor interactive latency T1 to T4. T1 is the touch to visual latency, T2 is the visual to network latency, T3 is the round-trip network communication latency, and T4 is the network to visual latency, but in another device. From the result, we see that similar application performance is maintained comparing between the LensCap integrated apps and the benchmark legacy applications. Furthermore, we identify negligible interactive latency overhead in T1, T2, and T4 for transmitting data in between processes, which is magnitudes lower compared with the network communication latency. Apart from previous quantitative analysis, we perform a user study to observe users' hands-on experience of LensCap integrated AR apps. Our user study consists of 5 activity interview phases, from preparation to app performance study, to privacy exposure awareness study, to LensCap introduction, and finally to LensCap data usage monitoring UI study. The user study reveals that users are aware of potential privacy exposure in the legacy apps, and they find that the current system cannot protect them. Also, LensCap integrated apps have similar smooth application performance from the user's perspective. And finally, LensCap can help them improve confidence while using untrusted AR apps. Therefore, altogether, LensCap split process application development framework can protect visual privacy and improve user confidence with negligible overhead in application performance and interactive latency. LensCap enables privacy-preserved continuous vision applications. However, it still has some limitations. Firstly, LensCap only provides services for verified third-party library APIs. In this paper, we demonstrate our system by implementing it around the Google AR Core library, though the implementation is generic to other libraries such as Apple's ARKit. For untrusted vision libraries, security experts could certify their operations through a scrutiny of source code. Secondly, the split process paradigm currently requires developers to rethink application development logic. However, a deeper integration of LensCap into AR development frameworks could enable the compilation process to make decisions of where functionality moves across the boundary for performance and efficiency. Thirdly, the LensCap system could also be extended to assist in securing visual offloading to cloud services. For example, we could verify that user data is sent to a cloud service associated with a verified URL address. Further verification would require certification that the cloud service only computes or stores the expected user data, but does not send information to other untrusted third-party entities. And finally, LensCap is currently implemented in Android and Unreal Engine environments. We're actively working on extending LensCap to other platforms such as iOS and game engines like Unity. To further ease AR developers' burden, we would like to build a community of support such that developers can find help and get trained to develop LensCap-adopted, privacy-protected, and user-trusted AR apps. In summary, we introduced LensCap, a split-process application development framework to protect users' visual privacy in cloud-based AR apps. LensCap isolates the processing of camera frames into a distinct visual process, meanwhile maintaining the cloud communication through another network process with the data transactions between split processes monitored and shown to users for approval at a fine granularity. LensCap enables AR apps and vision libraries to have expressive access to camera frames, their processing, and their rendering. Fine-grained user control of the potential transmission of real data between split processes, and detailed context provided to users regarding what data is sent to the cloud and at what times. Thanks for listening. If you are interested, please check out our paper.